Welcome back to the third session of Z transform. Previously we have seen an example of x of n equal to u of n, and now we'll extend that example with some modification. So now the second problem is x of n equal to a raised to n u of n. I have taken a number here a, which is a constant, then u of n is multiplied by a raised to n u of n. So now u of n is simple 1 from 0 to infinity. So depending upon the value of a, either this signal will increase from 0 to infinity if the value of a is greater than 1. If the value of a is equal to 1, then this is 1 raised to n, and 1 raised to n will be again 1. So again it will appear as u of n. If the value of a is greater than 1, then this signal will increase a raised to 1, a raised to 2, a raised to 3 and so on. If the value of a is greater than 1. If the value of a is less than 1, then this signal will decrease, because the very first signal will be at n equal to 0, because we are talking about u of n. U of n exists from n equal to 0. So when we multiply this, then this whole signal will appear from n equal to 0. So if the value of a is less than 1, for example we'll take it as 0.5, then the signal becomes 0.5 raised to 0, the very first signal, because n is from 0 to infinity. So 0.5 raised to 0 is 1, so 1 multiplied by 1 will be 1. If we take the second n, that is n equal to 1, then this will be 0.5 raised to 1. So 0.5 raised to 1 will be something like 0.5 itself. So we see that at n equal to 0 it was 0.5 raised to 0 is 1, n equal to 1 it is 0.5 raised to 1, that is 0.5, and n equal to 2 it is 0.5 raised to 2, that is 0.25, and so on. So we see that the value is decreasing as the value of n increases from 0 to infinity. So if the value of a is between 0 to 1, then the signal will decrease. If the value of a is greater than 1, then the signal will increase. If the value of a is equal to 1, then the signal will be simply 1, or u of n itself. So with this basic things, because we are not taking care of a raised to n, we take that the value of a is something like where the signal or the zt will converge. So considering that, we are going to solve this problem as it is. So x of n is equal to a raised to n u of n. We are not going to draw here a raised to n u of n, just we understand that the value of n is from 0 to infinity, because there is a multiplication of u of n with something. So we see that it is a right handed side sequence because of this u of n. So n is from 0 to infinity. So x of z can be calculated by the formula n equal to minus infinity to plus infinity x of n z to the power of minus n. This is a very simple formula that we have used earlier also. So if I substitute the value of x of n is a raised to n u of n. I will try to substitute this value instead of x of n. So we'll replace this x of n by this. So once I replace that x of n by a raised to n u of n, so the formula will become actually x of z equal to n equal to minus infinity to plus infinity a raised to n u of n z to the power of minus n. I have written it as 0 to infinity just because of this u of n. We know that when u of n appears in our question with the multiplication, then automatically the n will be ranging from 0 to infinity, because u of n exists only from 0 to infinity, otherwise it is 0. So the whole expression becomes n equal to 0 to infinity a raised to n u of n z to the power of minus n. We know that u of n is 1 between 0 to infinity. So instead of u of n, if I put 1, so this becomes a raised to n multiplied by 1 multiplied by z raised to minus n, or simply a raised to n into z raised to minus n. So x of z becomes now n equal to 0 to infinity a raised to n z to the power of minus n. If I take n as common, so if I put it in bracket, so this becomes a z inverse, a z inverse. If I take n only outside, actually it is a raised to 1 and z raised to minus 1. So a raised to 1 is a raised to 1 is a itself, and z raised to minus 1 is z raised to minus 1 raised to this n. I have taken it as a common part. So n equal to 0 to infinity a z inverse raised to n is what we are left with. Now we'll compare this with the standard formula. Now this is n equal to 0 to infinity, n equal to 0 to infinity, alpha raised to n, this is also alpha raised to n, and it is given as 1 divided by 1 minus alpha, where alpha now in our case is a z inverse. So the formula becomes 1 divided by 1 minus a z inverse. Instead of alpha we have written a z inverse. But what was the condition? The condition was very simple. Alpha should be less than 1, that we have seen in the previous session. The condition was alpha should be less than 1. So here also alpha is AZ inverse, so AZ inverse should be less than 1. Simple. AZ inverse should be less than 1. Now this will provide us the ROC. The condition for which the summation is existing always provides the ROC, because if the summation itself does not exist, then there is no question of ROC. Region of convergence itself means that the x of z exists, and if the x of z exists, so for what condition that x of z exists? So for in our case, x of z exists when AZ inverse, the magnitude of that AZ inverse is less than 1. So if I try to expand this, so x of z is nothing but 1 divided by 1 minus a by z, because this is z raised to minus 1. If I take it at the bottom, this becomes z raised to 1. So I am writing it as 1 divided by 1 minus a by z. Condition is AZ inverse must be less than 1. It is magnitude again. If I take LCM, then this is multiplied here. So z into 1 is z minus a divided by, whole divided by LCM is z. So it becomes 1 divided by z minus a divided by z. If I take this z on the top, so this becomes z divided by z minus a. Now x of z we have calculated it as z divided by z minus a. The remaining part is ROC. For ROC we are having this condition. So this is a divided by z, a divided by z. If I take this z at the bottom, this becomes z raised to 1. So a divided by z is less than 1. Now take this, add z on the RHS. So z multiplied by 1 will become z. So z, here we should get a magnitude. So make a correction of that. Magnitude of z is greater than a according to this condition. Magnitude of z is greater than a. Just I am writing it in the other way. Z is greater than a. Magnitude of z is greater than magnitude of a. The same thing is written in this form. There is no difference between these two expressions. So now this defines the ROC. So here it says that the magnitude of z must be greater than magnitude of a. So now the ROC exists for magnitude z greater than magnitude of a, means we should take a circle of radius a, and ROC is existing for z greater than a. Greater than a means outside the circle, because these are all the values which are greater than a. For example, this value is greater than a, this value is greater than a. So all these values which are like here are greater than a. So all these values are with magnitude greater than a. So ROC exists in this region. And if we try to calculate the poles and zeros, we know that if we equate numerator to 0, we get zeros. So if we equate z equal to 0, simply it is 0. And if we equate the denominator equal to 0, we get the poles. So z minus a equal to 0 implies z equal to a. So pole will exist at z equal to a. Again, if we try to look at very properly here, so ROC exists for z greater than a, and pole exists at z equal to a. So ROC is just beyond this a, just where a ends, immediately your ROC starts. So a does not exist, or a does not falls in ROC. This point A is never a part of ROC. It is actually away from ROC with a very minute space. So we can say that a pole is not falling into ROC, because pole is on the circle and ROC is outside the circle. So pole never falls on ROC. This is what we can understand from this again example. So thank you very much. We'll see you again in the next session.